Welcome back. Hopefully you have watched video one and reviewed your notes. We're just going to have a quick look now at looking at how we can depict equilibrium systems graphically. So you will have seen that we've used graphs to show how the rate of the reaction or the concentration of the reactants in the products changes as it moves towards equilibrium. So we're going to look at how we use those graphs and sketch those graphs because it's one of the things we need to be able to do when we're responding to equilibrium questions. So essentially the things that we need to be able to do in terms of interpreting or drawing these graphs are listed here. We need to be able to sketch graphs of rate versus time for a reaction to show when the equilibrium is established in a system. So the rate of the forward and the back reaction being equal at equilibrium. Sketch graphs of concentration of the reactants in the products versus time. Okay, so we really have to pay attention to what is on our vertical axes and our horizontal axes when analyzing these graphs. So we need to think about how our concentrations will decrease or increase as we approach equilibrium. And then identifying the equilibrium species of the system when they are constant. So this is a graph for the system for the production of hydrogen iodide from hydrogen gas and iodine gas to give 2HI. Okay, so if we think about this, initially when the reaction first kicks off, we're going to have hydrogen and iodide combining, so they're going to be colliding and reacting. As that happens, we will see that the hydrogen and iodine concentration is starting up here and it's going to decrease over time. Okay, so we can see that we've started with equal amounts of hydrogen and iodine and they're decreasing at the same proportion over time until this time point here. Okay, the red line is showing us the increase in concentration, because this is concentration of reagent on our y-axis, is showing the increase in concentration of the 2HI. So as this is being used up, the concentration will decrease, and as this is being formed, the concentration will increase. This occurs over time, so time is on our horizontal or x-axis here, until we can see that the concentrations no longer appear to change. At this point, it's where equilibrium has been reached. We have no visible change in concentration of the reactants or the products, okay? They're not equal, okay? So at equilibrium, we're not talking about equal concentration of reactants and products. What we're talking about is no apparent change in reactants and products, because once we've reached this horizontal point, this plateau in the graph, what is happening is that for every hydrogen iodide that is reacting, there is another being formed by the back reaction of the hydrogen iodide decomposing. So if we have a look now at using slightly different concentrations, okay, so now we are looking at the reverse reaction. So in this case, we're looking at the decrease in concentration of hydrogen iodide as equilibrium is established. So in this case here, we're now looking at the reaction from this perspective. Then we're going to look at the increase in concentration of hydrogen iodine as the equilibrium is established. So this time, because we're looking from the perspective of here, so we're starting with hydrogen iodide in our flask. Okay, then the concentration of hydrogen iodide decreases over time, and then the concentration of hydrogen and iodine gas increases over time. Okay, you will notice that they are still reaching the same equilibrium concentrations in this case. So when we're talking about these reactions, okay, what we're tending to talk about is what we refer to as the extent of reaction, and we'll talk about this a little bit more. But when we're talking about equilibrium, we're talking about the extent to which the reaction will occur in the forward direction or the reverse direction. If you remember back to acids and bases, when we talked about weak acids and bases, so something like ethanoic acid, we said it was an equilibrium between the ethanoid anion and H+. Okay, and what we said was that this species, the hydrogen ion being donated and the conjugate base of that, wasn't present in very much concentration. The reaction didn't occur very much. So what we're saying is that it didn't have a very big extent of reaction. It didn't move in the forward direction very much. Its preference is to be back on this side here. So with equilibrium, we are talking about the extent to which the forward reaction occurs, and there's a way that we can show that mathematically that we'll be looking at. So this is a summary quickly of all the things that we've talked about, okay? Remembering that when we graph equilibrium, when we're looking at concentration over time, we will have our reactants going down until they reach a plateau and our products coming up until they reach a plateau. In the case of rate, though, if we think about this, you can think that the rate of the forward reaction, if we think about the forward reaction, will go down as we use up the reactants, and the rate of the back reaction, so it will go up as we form more products. And then over time, they will reach the same point, okay? They'll always come to the same point, okay? Concentration graphs won't, but rate graphs will, because remember, by definition, the rate of the forward and the back reaction are equal at equilibrium. So if they reach equilibrium, then these two curves have to come to the same point. So just remembering that we need to note that equilibrium is dynamic, that we will only see equilibrium being reached in a closed system, so we have to be able to define our system, okay, that the concentration of the reactants and products remains constant at equilibrium, so this horizontal line that doesn't change. There is no change in macroscopic properties, so we can't visibly see a change. It will seem as though nothing is happening in the flask, but we need to remember something is always going on, and that equilibrium can be reached from either direction. Okay, so it can be from the reactants moving forward to the products, or from having products moving back towards the reactants. It doesn't matter, they will always come to equilibrium if it's a reversible reaction in a closed system. A note on this in terms of closed systems. We've talked about chemical reactions being reversible or irreversible, and how the particles need to collide to react, and then the product particles will do the same. This also occurs for state changes, okay? So when we're talking about freezing or evaporating, sublimation, if these occur in a closed system, they will also reach equilibrium. And if you think about it, we've just come out of summer holidays. You may have been to the beach, you might have had a wet towel, put the wet towel into a bag and sealed the bag. If you do that and leave it for a long time, the towel's never going to dry, because what's happening is, as the water molecules are evaporating out of your towel, they'll come up here and fill the flask with vapor. Because it's sealed, the water vapor can't escape. So those water molecules will start to condense back down. Okay, so you will then reach a point of equilibrium where you have molecules coming up, turning into a gas, and molecules condensing back into the water, and you will end up with this system so that your towel will never dry. It'll always stay wet, and then it gets moldy, and that's always bad. Okay, so remembering, always open up, don't keep them in tight sealed plastic bags in the heat. Okay, so when we do this, we need to check the states if we're looking at a physical equilibrium or if we're looking at a chemical equilibrium. Okay, because if we're looking at something like this with the equilibrium arrows, we can see we're going from liquid to gas here. It's telling us straight away that it's a physical equilibrium. Okay, so for our first two sections, you should now be able to define the characteristics of a closed or an open system in terms of matter and energy transfer. Explain reversible reactions in terms of the particle theory of matter, so collisions with sufficient energy, and talking about the concentration of particles as they collide and how that changes it. Define the conditions for equilibrium. Explain what is meant by dynamic equilibrium. That is something that you really need to be able to put into your own words, well structured for a test or exam response. And then sketch graphs depicting systems reaching equilibrium. in terms of reactants or products. So remembering when they're going to plateau and identifying that as T for equilibrium. You should also now be able to complete all the questions from the texts that are in our planner as outlined for 7.1. Okay, good luck, and I'll see you in class.